The voltage clamp technique, which was developed in the 1940s, has been key to our understanding of how the action potential is generated. As we've seen, voltage-gated sodium and potassium channels, which are responsible for generating the action potential, are both voltage-dependent and time-dependent. Therefore, it's very difficult to analyze their properties simply by recording an action potential, for after all, the action potential and the neuron changes voltage continuously at a function of time, and therefore it's difficult, if not impossible, to determine the properties of these channels at a specific voltage. The solution to this problem is to measure the properties of a channel at a fixed voltage, and this is what the voltage clamp technique does. So the voltage clamp in essence does two things. It measures the membrane potential of a cell and injects current into the cell to bring that membrane potential to a fixed value, to a value that is specified by the experimenter. And then at that fixed value, the circuit measures the current that is flowing into or out of the cell. And by measuring this ionic current, one can tell the state of the channels and whether the specific channels are open and closed, and what the kinetics of this opening and closing is. Now, I want to emphasize that while a neuron is voltage clamped, action potentials are not generated. One is recording the currents that lead to the generation of the action potential, but you're not actually recording action potentials because, after all, the membrane potential is fixed at a specific value. So the voltage clamp technique has been used over the years to determine the properties of voltage as well as ligand-gated channels, and the voltage clamp has been incorporated into the metaneuron program as well, so we can recreate some of the classical voltage clamp experiments. This circuit illustrates the basic principles of the voltage clamp technique, and I'd like to walk you through this circuit so you understand how the negative feedback circuit allows us to clamp the voltage of a neuron to a desired value, and how we can measure currents flowing through open channels in the neuron. What we see here is the neuron we want to voltage clamp, and we are inserting two electrodes into the neuron to measure voltage and to inject current. What is illustrated here are classical sharp electrodes that are inserted into the cell, but the voltage clamp technique can also use patch electrodes, whole cell patch electrodes, to measure voltage and inject current, or there is a variant of the technique where a single whole cell patch electrode can be used to voltage clamp a cell as well. Now let's say we want to clamp the voltage of the cell to 0 millivolts. The way that is done is the experimenter applies a 0 voltage, the voltage we want the cell to go to the positive input of a differential amplifier. This is an amplifier that has a positive and negative input, and the output of this amplifier is the difference in voltage applied to the two inputs. So we want to clamp the cell to 0 millivolts, but let's say initially the cell is sitting at plus 5 millivolts. So this electrode here measures the plus 5 millivolts, which goes into the negative input. We are applying 0 millivolts, the desired voltage, to the positive input. If we have plus 5 going to the negative input and 0 to the positive, the output of the amplifier is negative. So a negative voltage comes out of the amplifier. This voltage goes into a voltage to current converter, and a negative current comes out of this voltage to current converter. So this negative current is then applied to the second electrode, the current injecting electrode. A negative current injecting negative charges into the cell will hyperpolarize the cell and will lower the voltage from +5 until it gets down to 0, which was our desired voltage, at which point the electrode will measure 0 millivolts going into the negative input. We have applied +0 millivolts to the positive input, and therefore 0 volts will come out, and then we will be injecting no more current. So this is a negative feedback circuit, and it serves to clamp the neuron to the voltage that we apply to the positive input here. So we can specify a voltage, and then the current injection will bring the neuron to the desired voltage. Now let's say we want to do an experiment where we first hold the cell at minus 80 millivolts, and then at time equals 0, we quickly step the cell to 0 millivolts. So initially we would apply minus 80 millivolts to the positive input of the amplifier, and then the appropriate current would be injected into the cell to bring the cell and hold the cell at minus 80 millivolts. Then at time equals 0, we quickly switch the voltage going to the positive input from minus 80 to 0. Now the cell is still sitting at minus 80, so minus 80 is going into the negative input. We now have 0 going into the positive input, and this results in a large positive voltage coming out because there's minus 80, which is inverted by the negative input. So a large positive voltage comes out of the amplifier. This is converted to a large positive current, which is injected into the cell, and very rapidly, in less than a millisecond or even 100 microseconds, the voltage inside the cell is raised from minus 80 to 0. Okay, so now at time equals 0 and times beyond that point, we now have clamped the cell to 0 millivolts. Well, things will just remain constant as long as nothing else happens. However, if this neuron expresses voltage-gated sodium channels, we know that when we step the membrane potential of the cell from minus 80 to 0, these channels will open after a very short delay, and sodium ions, positively charged sodium ions, will flow into the cell. This will raise the voltage. Remember, we've clamped the cell at 0 millivolts, but sodium flowing in will try to raise the voltage above 0 millivolts. This amplifier, the electrode and amplifier, will sense this and immediately inject a negative current into the cell to just balance out the positive ion charge that's flowing in through the voltage-gated sodium channels. And in fact, this negative feedback circuit will continue to just match the influx of sodium. Now we can monitor how much current is being injected into the cell here, so we have a measure of how much sodium is flowing into the cell. And in that way, we can determine the time course of the opening of the sodium channels and how many sodium channels are being opened. By the way, we can now understand the convention that a positive influx of ions into a cell, for instance sodium flowing into the cell, is sensed as a negative current using the voltage clamp technique, because when sodium flows into the cell we have to inject a negative current to just balance it out, and therefore with the opening of sodium channels and the influx of sodium, this is measured as a negative current by the voltage clamp technique.